Hello, everyone. Welcome to today's live broadcast, Top 3 Easiest Ways to Boost Your UHPLC Chromatography Performance for Biomolecule Analysis. I'm Jeannie Linky Northrup, the Special Projects Editor of LCGC, and I'll be your moderator for today's event. We are pleased to bring you this webcast presented by LCGC and sponsored by Advanced Materials Technology. Advanced Materials Technology is an innovative product development and HPLC column manufacturer focused on improving the presentation of the sample to the detector. From pioneering fused core technology in 2005, the Halo product line has changed previous conventional wisdom that high resolution requires high back pressure. Now, in its 17th year, AMT continues to be a leader in novel superficially porous particle development, enabling high efficiency and reliability for scientists involved in both small and large molecule separations, and delivers application-specific solutions designed to meet industry challenges. Before we begin with today's presentation, we just have a few important announcements to make. This webcast is designed to be interactive, and we encourage you to ask your questions throughout the event. You can submit questions by typing them in the Q&A box, which can be found at the bottom of the video player. You can enlarge the slide window by clicking on the small icon in the bottom right corner of the media player. The slides will advance automatically during the event. If you experience any technical problems viewing or hearing this presentation, please click on the question mark help widget in the top right of your presentation window. I would now like to introduce today's speaker. I'm pleased to be joined today by Dr. Stephanie Schuster. Dr. Stephanie Schuster earned her PhD under the guidance of Professor Joe P. Foley at Drexel University. She joined Advanced Materials Technology, AMT, in June 2009 as a research scientist, working with Dr. Jack Kirkland, providing contributions to the commercial development of products designed for peptide and protein separations. Most recently, as part of the technical support team at AMT, Stephanie has been providing customer support in optimizing and troubleshooting their applications. Stephanie, thank you so much for joining us. Please get us started.
Thanks so much for the introduction, and thanks to all for attending today. So today I'll be talking about the top 3 easiest ways to boost UHPLC performance for biomolecule analysis. First, you want to select the appropriate acid modifier for your analysis. Next, you want to optimize your UHPLC system dispersion. And third, use a Halo 1.5 mm ID column. We'll begin with a discussion of choosing the acid modifier for your analysis. For acid modifier choices, trifluoroacetic acid, or TFA, is a common choice for peptide and protein analysis when using UV detection. It is an ion-pairing agent and has a low pKa. We have it listed as not recommended for MS detection because of its impact on ionization efficiency. It causes ion suppression, and it can be difficult to remove from the LC system components, including the degasser, column, and MS source. Of course, there are those who use TFA at low concentrations, and they are able to get good results, but usually these systems are dedicated to being used with TFA for a specific assay. Difluoroacetic acid, or DFA, offers a compromise in that it is not as strong an ion pair reagent, so there is not as much ion suppression as you see with TFA. We recommend it for both UV and MS detection. And finally, formic acid is a common choice for MS detection because it gives great ionization efficiency, but it can cause poor peak shapes since its pKa is higher, so the pH will be higher compared to TFA and DFA. And of course, formic acid is not an ion pair reagent. Now let's look at an example of these three acid modifiers when used with UV detection for an intact monoclonal antibody. The monoclonal antibody analyzed here is trastuzumab. The top trace in blue used 0.1% formic acid. You can see that the peak width is 0.255 minutes, and it shows the least retention. The middle trace in orange used 0.1% DFA. The peak shape is symmetrical, and the peak width is 0.095 minutes, which is much narrower compared to the result with formic acid. The bottom trace in black used 0.1% TFA. Peak width is 0.087 minutes, and this result shows the highest retention. The zoomed-in sections show the minor MAB components and how the selectivity is influenced by the DFA and TFA in the mobile phase. In these panels, we have compared to a 300 angstrom fully porous particle column, again using trastuzumab and UV detection at 280 nanometers. Both columns are C4 stationary phase. We have adjusted the gradient conditions so that the retention times are comparable across the three different acid modifiers. The top left panel shows the results with 0.1% TFA. The peak width of the Halo 1000 angstrom column is taller and narrower compared to the 300 angstrom FPP column. The bottom left panel shows the results with 0.1% DFA. Again, the result with the Halo 1000 angstrom column is a taller, narrower peak compared to the 300 angstrom FPP column. Next, focus on the bottom right-hand panel, which shows the results with 0.1% formic acid. Both columns show broader tailed peak shapes, but the Halo 1000 angstrom column performs better than the 300 angstrom FPP column. In the top right-hand panel, the formic acid has been increased to 0.25%. This results in a sharper peak for the Halo 1000 angstrom column, but not quite as sharp as was observed with the TFA and DFA conditions. Let's now look at mobile phases for improved protein LC-MS. In these experiments, we used a Halo 400 angstrom C4 column in 2.1 by 100 millimeter. Our mix of proteins included ribonuclease A, recombinant ubiquitin, lysozyme, apomyoglobin, and enolase. The UV results are on the left, while the MS results are on the right. For the 0.1% DFA results in the UV column, you see sharp peaks and the most retention, but moving to the TIC results, we see hardly any MS signal due to the ion suppression of the TFA. For the 0.25% formic acid results, we see tailed peak shapes for ubiquitin, myoglobin, and enolase. However, the TIC results with 0.25% formic acid show the highest response compared to TFA and DFA. 0.1% DFA results show slightly less retention compared to the TFA, but more retention compared to formic acid. In terms of the TIC, there is more signal compared to TFA, but not as much as with formic acid. For a compromise in terms of peak shape, retention, and ionization efficiency, DFA is our recommendation for LC-MS analysis. The same trend can be observed for the comparison of UV and MS intensities using a peptide synthetic mixture. In these comparisons, we used a Halo 160 angstrom ESC18 column in 2.1 by 150 millimeter. The mix of peptides consisted of leucine and kephalin, angiotensin 1, substance P, melatonin, and beta endorphin. All the acids were used at a concentration of 10 millimolar. Starting at the left-hand side with the formic acid results, we see UV results with a tailed melatonin peak, indicated by the letter M, but a strong TIC signal. In the middle panel with the TFA results, the UV peaks are sharp and narrow, but the TIC signal is significantly diminished. In the final panel with the DFA results, we see a good compromise of narrow peaks in the UV and sufficient response for the TIC. In summary, the formic acid gives wider peaks and tailing. TFA gives 20 to 50-fold lower MS signal, and the DFA gives 2 to 4-fold lower MS signal with sharp peak shapes. In terms of an acid modifier summary then, all three acid modifier choices can be used with UV detection. As we observed, the peak shapes can show tailing with formic acid. For MS detection, TFA is not recommended because of its ionization suppression. DFA offers a compromise for symmetrical peak shape and good ionization efficiency for MS detection. Now let's shift the discussion to how to optimize your UHPLC system dispersion. Total band broadening or dispersion. Here we have a simple diagram of a UHPLC system. The portion in the black dashed section represents the total dispersion. Now we have highlighted the sources of extra column band broadening. The pre-column portion is highlighted in yellow and consists of the sample injector and the pre-column tubing. The post-column portion is highlighted in red and consists of the post-column tubing and the flow cell or the ionization source, depending on the detector. And what I'd like to point out here is depending on whether your separation is using isocratic or gradient conditions will really determine how much impact the pre or the post extra column band broadening will affect the separation. So if you're running under gradient conditions, usually you get some benefit of sort of sharpening of the sample plug as it hits the head of the column. So in that case, the pre-column broadening or tubing doesn't really impact the separation as much. And what you would really need to focus on is the post-column tubing and either the flow cell or the ionization source. Now I would like to take a moment to talk about the relationship between extra column dispersion and extra column volume. ECD can be calculated by taking the square of the quantity of the extra column volume divided by 4. So for example, 2 microliters squared of ECD equals 5.66 microliters of ECV. The ECD is measured in microliters squared, while the ECV is measured in microliters. It's much easier to visualize ECV, but it's more useful to know ECD since this value is an additive portion of the total dispersion in the system, which includes the column, which this is the total dispersion in the system equation, and you can see that consists of the pre-column dispersion, the dispersion from the column itself in the middle, and then the post-column dispersion. So what are the pros and cons in shifting from 2.1 millimeter ID to 1 millimeter ID? On the left is a separation of alkyl phenones using different column IDs. The 2.1 millimeter is shown in blue, the 1.5 millimeter is shown in orange, and the 1 millimeter is shown in black. We injected the same concentration and injection volume on all 3 columns. Here you can see a zoom in on the third peak on the right-hand side of the slide. While the 1 millimeter trace in black gives the highest response, it also has the lowest plates at 7,600. The 1.5 millimeter and 2.1 millimeter have similar plates, but the signal for the 1.5 millimeter column is higher. This is caused by 2 effects. Since the 1.5 millimeter ID column is run at half the flow rate of the 2.1 millimeter ID column, the sample spends twice as much time in the detector flow cell. Additionally, because of the smaller volume column of the 1.5, the sample is diluted less than with the 2.1 millimeter ID column. In the move from 2.1 millimeter ID to 1 millimeter ID, the signal does increase, but there is a significant loss in efficiency, primarily due to extra column effects. 1.5 millimeter ID columns can provide a compromise between these effects. So you may be wondering, how do I estimate extra column dispersion? In the 4-part series in LCGC North America from Dwight Stoll, Thomas Lauer, and Ken Brockhoven called Where's My Efficiency Gone? Impacts of Extra Column Peak Broadening on Performance, there was a link to an online dispersion calculator provided, which I have here at the top of the slide. This is what we use to generate the pie charts on the right-hand side of this slide. All you have to do is input the specifics for your separation and the UHPLC, including the connecting tubing IDs and lengths. The dispersion from the column is in yellow, the dispersion from the post-column tubing is in blue, and the dispersion from the detector is in gray. So these particular experiments are done under gradient conditions, so there would be no impact from the pre-column tubing. In this comparison, we used our standard plumbing with the results shown in the blue trace, and then optimized the system for the results shown in the orange trace at the bottom. We were able to increase the peak height from 66 milliAU to 105 milliAU, and reduce the peak width from 0.046 minutes to 0.037 minutes. This was done by using a low dispersion flow cell with a smaller ID and shorter length connecting tubing. Speaking of tubing, there are several vendors that offer zero dead volume connectors. AMT has partnered with IDEX to offer the Marvel Exact connectors. These connectors have a flat sealing face instead of a ferruled fitting. Sometimes the ferruled fitting can introduce dead volume if the capillary is not properly seated in the column or injection port, and that's indicated by that yellow section where it says extra internal volume. The Marvel Exact connectors give an audible click when they are properly tightened, and you can feel the click, so it's less likely that you would over-tighten them. They're available in both peak sill and peak line stainless steel options. And for going from the column outlet to a mass spec source, we recommend the peak sill. And if you're using, if you wanted to change the tubing from the injector to the inlet of the column, we would recommend the peak line stainless steel option. The volume is included with the dimension for easy selection. So, for example, a 75 micron by 600 millimeter connector has a volume of 2,650 nanoliters. Now, as a summary to the dispersion section of this presentation, I'd like to present this Van Deemter comparison of a Halo 1.5 millimeter to a Halo 2.1 millimeter ID column. You can see with the combination of well-packed 1.5 millimeter ID columns and a low dispersion UHPLC, the efficiencies of 2.1 and 1.5 millimeter are comparable. We estimated the dispersion for this particular UHPLC to be 2 microliters squared, just for reference. And now finally, I know I sort of hinted at using a 1.5 millimeter ID column in the last section, but I'd like to now discuss in particular how using 1.5 millimeter halo column can boost your UHPLC performance for biomolecule analysis. So what are the benefits of 1.5 millimeter ID columns? These columns basically bridge the gap between analytical and microflow systems. What you see is more sensitivity from conventional UHPLC systems, higher ionization efficiencies from LCMS systems, reduced solvent consumption compared to 2.1 millimeter ID columns and greater, and this is particularly important for those concerned about reducing their chemical footprint. And an easy to implement microflow solution with existing systems. So what I mean by that is there's no need to spend the money to buy a specialized capillary system in order to boost your results. So here's a protein separation with UV detection, comparing a halo 1000 angstrom C4 in 1.5 by 150 millimeter dimension. And those results are on the top in the blue trace, and it was run at 0.2 mils per minute, compared to a halo 1000 angstrom C4 in 2.1 by 150 millimeter. And those are the results in orange on the bottom trace. We injected 2 microliters of the same concentration protein mix for both columns. And on average, we're seeing double the peak areas with the 1.5 millimeter ID column. The peak heights are approximately 1.7 times taller with the 1.5 millimeter ID column. And if we were able to reduce our dispersion even more, we would expect the peak heights also to be, on average, 2 times bigger. Next, I will be showing some LC-MS comparisons. These results are taken from the recently published Journal of Chromatography A paper from Vibert et al., where the flow rates were scaled and the gradient delay was taken into consideration. And in all these examples, we injected the same volume and concentration on all the columns. In this example, the area of trastuzumab is 3.3 times larger on the 1.5 millimeter ID column, and the peak height is increased. So the results of the 1.5 millimeter ID are here in black, and the 2.1 millimeter ID results are shown in blue. And you can see how much taller the peaks are on the 1.5 millimeter ID column compared to the 2.1. For the charge state envelope comparison for intact trastuzumab, the overall shape characteristics are not vastly different. For the most abundant charge states, the pattern is slightly different. And you can see the 1.5 millimeter results are on the top compared to the 2.1 millimeter results on the bottom. For the subunit MAB in which trastuzumab was reduced and alkylated, we have here the comparison of the 1.5 millimeter ID results in black on the top compared to the 2.1 millimeter ID results in blue. The heavy chain area is 2.1 times larger on the 1.5 millimeter halo 1000 angstrom diphenyl column. The light chain area is 2.4 times larger on the 1.5 millimeter halo 1000 angstrom diphenyl column. So we're seeing the same trend as what we had seen with the intact trastuzumab. For IDES digested trastuzumab, again, the 1.5 millimeter results are here in black, and the 2.1 millimeter ID results are shown in blue. The FAB area, which is the second eluting peak, is 2.7 times larger, and the FC area, which is the smaller first eluting peak, is 3.1 times larger. For the charge state envelope comparison, first the FAB is shown on the left-hand side, with the intensity being greater with the 1.5 millimeter results. That's shown on top compared to the 2.1 millimeter ID results. Then for the FC fragment, which is shown on the right-hand side, you can see the intensity is significantly greater with the 1.5 millimeter ID results compared to the 2.1 millimeter ID results. So going back to the dispersion discussion we had earlier, let's look at the FAB peak shape comparison on a 1.0, 1.5, and 2.1 millimeter ID halo columns. So you can see, while the signal is most intense for the 1 millimeter ID column, the peak shape is broad, and that 1.5 millimeter ID column offers a compromise between increased signal and sharper peak shape, which is shown here in the middle of the slide. And the 1.5 result is in the blue trace, compared to the 2.1 millimeter ID result, which is in the pink trace. So you can see how the dispersion is really impacting the 1 millimeter ID column more so than the 1.5. Now I'd like to discuss a peptide map comparison showing the 1.0, the 1.5, and the 2.1 millimeter ID Halo 160 angstrom ESC18 columns. So the pink trace, we had implemented no delay for the 1 millimeter ID. There was a half-minute delay used for the 1.5 millimeter ID column, and a 1.7 minute delay used for the 2.1 millimeter ID column. These are all scaled to the same intensities, and you can see how the peak intensities are increasing as we decrease the column ID. We extracted the ion current for some particular peptide fragments, and these are shown here by charge state. So on the left-hand side, the charge state is 2, and on the right-hand side, the charge state is 3. So you can see going up from the bottom with the 2.1 millimeter results, the signal intensity is increasing with the 1.5 millimeter ID column, and with the 1 millimeter ID column, it's not quite as intense, and that's due to the dispersion effects that the 1 millimeter column is impacted by. And that, depending on the charge state, whether it's the +2 or the +3, you can see the impact on the extracted ion current intensities. We've combined this on one slide. So now for the heavy chain fragment number 11, what we did was we now are showing the 1.5 millimeter ID result in the middle is giving the most intense peaks for the 3+ charge and for the 2+ charge compared to either the 2.1 millimeter ID or the 1 millimeter ID result. In terms of reduced solvent consumption compared to 2.1 millimeter ID columns, we're running at half the flow rate compared to a 2.1 millimeter ID column. So what that means is we're saving 50% of the solvent. So just by running at the reduced flow rate for that particular 1.5 millimeter ID dimension, you can save half of the solvent, and also that would translate to the solvent lasting longer and reduce solvent disposal cost. This is an easy to implement microflow solution. So the columns look and feel like a 2.1 millimeter ID column. One way to be able to distinguish them from our 2.1 millimeter ID columns is that they have these streamlined end fittings, which indicates that it's a 1.5 millimeter ID. The Halo 1.5 millimeter ID columns are available in chemistries and pore sizes for small molecules, peptides, and proteins. So in this particular presentation, I focused mainly on the peptides and proteins, and those would be the Halo 160 angstrom ESC18 and the Halo 1000 angstrom C4 and Halo 1000 angstrom diphenyl. So for the summary of this section, I've shown more sensitivity from conventional UHPLC systems, higher ionization efficiencies from LCMS systems, reduced solvent consumption compared to 2.1 millimeter ID columns, and that's important for those trying to reduce their chemical footprint, an easy to implement microflow solution with existing systems. They're made by a trusted manufacturer of U-score columns in a 9001 ISO certified facility, and they're available in chemistries for small molecule, peptide, and protein separations. In terms of conclusions, just a reminder of our top 3 easiest ways to boost UHPLC biomolecule analysis performance. First would be to use DFA modifier for your analysis if you're using LCMS. Optimize your UHPLC system dispersion. And finally, use a 1.5 millimeter ID halo column. I have a few acknowledgments I'd like to make. I'd like to thank the team at Advanced Materials Technology, including Ben Liebert, Connor McHale, Peter Pellegrinelli, and Stephanie Rosenberg. I'd also like to thank our collaborators, Jim Grinius at Rowan University, Justin Godino at GSK, Mark Schur at Crown Gold Analytical, and Thomas Wakey. To find more information on 1.5 millimeter ID halo columns, there was a poster presented at HPLC 2022, and that's available on the Halo website. And there have been 2 journal articles published, both in the Journal of Chromatography A. A lot of the examples that I presented today came from the first paper by Liebert et al. And then the earlier paper from 2021 was with our collaborators in Europe. Thank you for your attention, and I'd be happy to answer any questions you might have.
Thank you, Dr. Schuster. That was a really informative presentation. Truly appreciate the time that you've put into this presentation today. Before we get started with our question and answer session, I would like to remind our audience how to submit your questions and remind you that it is not too late. You can submit your questions by typing them in the Q&A box that can be found directly below your video player. Stephanie, I think that leads us into our discussion. It does look like we've had quite a few questions come in from the audience during your presentation, so let's begin.
Okay.
The first question is your column ID, and it increases your sensitivity. Why not use the 1 millimeter ID or less?
Oh, right. So if you have a system that has small enough dispersion, we are able to get the optimum performance from 1 millimeter ID or less, then I would say definitely do that. But in general, the usual UHPLC systems don't have low enough dispersion, and they're also not able to operate at such low flow rates without going to a specialized pump. So that's why we feel that the 1.5 millimeter ID is really a good compromise for people with UHPLCs who want to use less solvent and also see the increased signal intensity when you inject the same amount as you would on a 2.1.
Okay, as you're mentioning, both 1.5 and 2.1 ID columns, what is the effect on sample loading when moving from the 1.5 to the 2.1 millimeter ID column?
Sure. So the sample loading, just like we have the flow rate going from a 2.1 millimeter ID down to a 1.5 millimeter ID, the sample loading would also be halved. So,
okay, makes sense. Let's see what else. You still see an increase in performance if you used an unoptimized system?
sure. So if you were using an unoptimized system, what would happen is, of course, you'd be still saving solvent because you're operating at a lower flow rate, but you may or may not see an increase in performance. Just really depends on how much extra column volume is in your system.
Okay. Our next question, can you recommend some tubing convention for pre or post column dispersion?
Oh, sure. So in general, I would recommend the pre-column tubing to be either 75 micron or 50 micron ID, and then the length, that really depends on the distance from, say, your sample injector to the inlet of the column. So that length, I try to make that as short as possible, maybe 350 millimeters or less. And then in terms of the post-column tubing, again, I would, depending on your system pressures and what conditions you're operating at, I would either go with, again, 75 or 50 micron ID. And then the length also, again, is going to depend on how much distance there is between the outlet of the column and whatever detector you're using, whether it's UV or mass spec, or if you're going from, say, the outlet of the column to a mass spec diverter valve or into the source. So you would have to measure that length, but don't go longer than that.
Okay, good to know. Now let's talk about a little bit of what you've researched. Have you looked at all mixed acids? Something that was brought up as an example, 0.1% FA with 0.01 DFA as a compromise? Oh,
that's a really great question. We have not had a chance to look at that, but I am really curious how that ionization efficiency would be impacted. I mean, I would expect it to be, some better peak shape, because I do know that some people mix TFA and formic acid. So the mixing of formic acid with DFA, I think, could be really interesting.
And talking about some of the additives that you've explored, did you look at ammonium formic acid additives?
Yes, we did look at that. I didn't present the data here, but I'd be happy to share the paper where we looked at those additives.
Okay, great. Maybe we can ask the viewers if anyone is interested in that paper that they can follow up. I know you mentioned a connect feature at the end of your presentation to contact, but that would be great that you'd be able to share that over with those parties that are interested. So let's talk a little bit about some of the issues we're having in the market. A question that came in discussed facing pressures to reduce solvent consumption based on shortages. Will the 1.5 millimeter ID column help with that?
Definitely. Well, and the main reason is because you're using the smaller ID, you'd be operating at a lower flow rate, so you wouldn't be using as much sample solvent, and then so the sample solvent could potentially last you 50% longer if you were going from a 2.1 down to the 1.5. And then also, you'd be spending less on waste disposal cost.
Great. And I know you did start to allude to this, but another question just popped in, so maybe you can remind our audience that someone asked, isn't it true that smaller ID columns have lower efficiency?
Oh, sure. So we have spent a lot of time and energy optimizing the loading of the 1.5 millimeter ID columns. So while in general you might expect less performance as you go to smaller ID, we have really tried our best to get as much performance out of that particular hardware design that we have for the 1.5. So I had shown the Van Deemter plot where the minima are really equal for the 1.5 compared to the 2.1.
Now, another question that did just pop up. This scientist has the Waters 1 class system, and they would like to know if the Halo 1.5 millimeter works with that system.
Oh, sure. So it definitely would work. The only thing I would caution is if you're using a hard fitting, you probably have to make sure that the fitting is really bottoming out in the inlet and the outlet of the column, because sometimes the depths of different columns from different column vendors can be different. So you just have to, properly seat the column, and then you'll be good to go.
Okay, I know we do have a few moments left. While we are just reminding viewers that it is not too late to submit their questions, Dr. Schuster, I would just like to ask, based on some of the Q&A questions that came in, if there is anything else that you'd like to mention to our participants today.
Oh, sure. So I'd like to just sort of point out that all of the examples that I had shown in the presentation were using the same injection volume and the same concentration. And the reason we had done that is because we really wanted to show that you could get more signal with the 1.5 millimeter ID columns. But if you're, say, sample limited, the good news is you can scale the injection volume. So instead of using a 2 microliter injection, you can say use a 1 microliter injection, and you would get the same sort of response as you were getting on your 2.1 millimeter ID. So if you're sample limited in any way, that would be another advantage of going to the 1.5 millimeter ID.
Great. Thank you, Dr. Schuster. Again, appreciate your time. I'd also like to thank the audience for their time in attending and participating in today's event. I would like to thank our sponsor, Advanced Materials Technology, for making today's educational webcast possible. We would like to ask everyone in the audience to participate in a brief survey. The survey will appear on your screen after today's presentation has concluded. You will receive an email as well, alerting you when this webcast will be available for replay. We invite you to forward that announcement to any of your colleagues who may have missed today's live event. We thank you all for joining, and we'll see you next time. Goodbye.